So whenever anyone tries to sell you a learning algorithm, one of the things you might want to ask, besides how fast is it and how much memory does it take, is what can it learn? Right? So if somebody gives you a learner that can only learn extremely simple, stupid things, you might not be very happy with that learner. The nice thing about, so the technical term for this is what's the hypothesis class that the learner is searching in. You can think of the learner as being given this data and then trying to find a hypothesis that matches the data. I mean, really, when you think about it, all we're doing in supervised learning is regression. You've probably heard the term linear regression get flown around. In fact, you all took statistics classes, so of course you know all about linear regression. You know, you have some state variable x, and someone shows you some examples and says, "Hey, when x was here, y was there. When x is here, y was there. When x is here, y was there. When x is here, you know, learn the concept." And this concept is really well captured by a line. So linear regression is a very popular regression formalism, but it can only learn things that are linear, that are lines. So it's a fairly limited learner. If you think about this, so this is a one-dimensional problem. Let's go to a two-dimensional problem. A two-dimensional problem, here's x1 and here's x2, and maybe we're doing classification. So this is regression where you're trying to learn a real valued output. Here we're trying to do something. Let's just pretend we're doing classification with a binary decision, like is it a chair? And like, yes, that's a chair. Yes, that's a chair. That's a chair. We have all these examples. Those are chairs. Fantastic. And oh, that's not a chair. That's not a chair. That's not a chair. These things are not chairs. So if you have a linear, if all you can learn is a linear function, you can imagine a two-dimensional linear function, a plane. And now I'm not exactly an artist, but let's pretend that we have this plane shooting out of the piece of paper. So it's above the paper here, and it kind of shoots in that way. And the part that's below the paper is this upper part here. So this part is above the paper, and then it shoots down and goes below. That's called that's a linear classifier, and the boundary where the plane cuts through the paper is going to be a line. Like no matter what plane I learn, it's going to cut through the paper in some line at some orientation. Right? If I'm learning a plane, all I can do is I can tilt it any direction I want, but it's going to learn some kind of line. And that's a problem with learning linear functions. Is all you can learn is lines. The nice thing about k-nearest neighbor is it's extremely expressive. And Matt claims that he showed you an example of this on Wednesday, where let's say I have x1 and x2, and these things are all chairs. Absolutely. But what if these things are not chairs? All around here. And then down here, well, there are some more chairs. Let's pretend this is perfect, error-free data. We had a graduate student do this instead of some undergraduate. And it's absolutely perfect data. So this is like the world of chairness. It's like you can be a chair if your x1 is here and your y2 is there, or if your x1 is over here, no matter what your x2 is. So this is a very complex hypothesis. And something like a 1 nearest neighbor or a 3 nearest neighbor learner can learn this no problem, as long as you have enough data. Because it's going to just, wherever the new instance comes in, if the new instance comes in right here, well, pretty easy. Look, the closest thing there, closest thing there, closest thing there. Like, get my 3 closest. I'm a chair, dude, right there. It's clear. So the decision boundary of the classifier is going to be this this thing here, let's pretend we're doing one nearest neighbor learners. So that means the decision boundary is going to be exactly halfway between a positive example and a negative example. Because if we're any closer to one or the other, then that's the way it would get classified. So that's the decision boundary we can learn with a nearest neighbor classifier. It's extremely complicated. So that's one advantage of nearest neighbor learners, is they're very expressive. They can learn a very complex hypothesis. Everyone understand what I was just saying? All that jargon? Yeah?
If you take one of those points and figure out whether or not it's chairs that get at the knowledge base?
Well, if you say, oh, teacher, I think this is a chair, and the teacher says, my son, yes, that is a chair, then absolutely, the word has come down from above. That is a chair, now you know. There's a wonderful, very exciting area of machine learning called semi-supervised learning, where someone gives you a few chairs and then puts you in a furniture store. And you're like, I barely know what a chair is. What the hell are you trying to do to me? And so the question is, can you bootstrap from the few things that you know to do better learning than if you just had the labeled examples only? I usually don't talk about this for like another week. So a very wonderful question. So one thing you can do is you can take the thing that's closest to an example that you've seen, and if you're really comfortable saying, it's that exact same chair, it's got gray fabric on it. But I know fabric isn't super important, given what I've learned so far about chairs. It mostly has to do with whether there's a back support thingamabobber, and there certainly is. So I'm comfortable saying that is a chair, and now I retrain my classifier. And now maybe even there are more examples that are well within the decision boundary. Like I'm very certain that these are not chairs and that these are chairs. So then you're bootstrapping up using those examples. So this is called semi-supervised learning, because someone gave you a little bit of supervision. That's kind of like a 700 level class. Someone stands up here and gives you a lot of hot air about the algorithm kind of works like this, and you're really expected to just go and figure it out to the point where you can really implement it. So
this is a 700 level class.
I'm sorry?
This is a 700 level class.
Exactly.
Okay.
I hope you feel as if I haven't been holding your hand the entire time.
So when you're doing that, I would assume every time you make any sort of jump and say, oh, I think with reasonable confidence this is a chair,
yeah,
and then I'm going to assume that and readd it to my knowledge base, it seems like you're going to be accumulating a little bit of error that is, when they're doing that,
potentially.
Do they try to mathematically bound that error and not go beyond a certain bound?
Yeah, there's all kinds of math in machine learning, of which we're going to do like none. So ask that question again when we come to what's called boosting, which I don't know if we'll get to on Wednesday. Maybe it's what the grad students have to do for the assignment 5. They have to implement boosting. So it'll come up then. What?
And I don't know why you pluralize grad students.
Neither do I. Wishful thinking, I don't know. You are the power of more than one person, Frank. Well, for a while we had someone else in the class who was taking it as a grad student as well. Okay, so the fancy word for the area that is defined by being equidistant between specific points. So if I put a few dots down, the computer graphics people have thought about this a lot. I love drawing these things. If you ever get bored, I highly recommend just sitting around and drawing these things. Exactly. Okay, so that's called a Voronoi diagram, and that's that's how you can figure out who's closest. The closest example. These are going to be straight lines. It's just all kinds of beautiful stuff happens in here. I just wanted to say that word when we were talking about k-nearest.
Multidimensional calculus and get into conjugate gradient stuff.
No, we're going to talk about gradients in just a few minutes, but for calculating these things, yeah, I don't know how you calculate these things. There is something about how you look at like quadratic functions coming up in the extra dimension, but I don't know. Don't ask me.
For our purposes, though,
Mhm.
aren't those just like conceptual ideas?
Yeah, you don't have to implement this kind of a thing at all. I just wanted to give you an idea of how does a nearest neighbor algorithm work. What do the decision boundaries look like? And they are going to be Voronoi diagrams.
But we never actually calculate a decision.
Boundary, no, you don't.
Dynamically
You just
say,
find the nearest instance. Yeah. But it's kind of fun to know what's happening, I think. As a good engineer, we should know how our stuff works.